Yeah, so as just mentioned, I'm an application security engineer at Box. So in my role, I am fixing vulnerabilities, building security frameworks to help other engineers write secure code, and doing education, training, and outreach to make sure that all the developers at Box understand security and are able to use those frameworks effectively. I wanted to start off with a quick poll. Who here writes code, makes software? All right, who here deploys code, maintains code, configures it? Not so many. All right, who here likes to break stuff? All right, you guys make my life miserable. No, seriously, I actually like my job a lot. That's true, a lot better. So I'm currently working at Box. I've been there about a year and a half. Prior to that, I was at Symantec for some time, working in a variety of different roles, working with network security, remote access, authentication, anti-spam, web security. Prior to that, I was at SafeWeb, which was acquired by Symantec. SafeWeb was at one time the world's largest internet privacy service. It was also the company, or one of the companies that invented the SSL VPN technology that so many of us use today. Before SafeWeb, I was doing my education at Caltech. It's an amazing place like no other, and primarily I was learning how to learn. I hope that all of you will be able to learn something interesting and useful today. So I'm going to talk about web security, specifically HTTP headers that can be used to secure web applications. These have come up over time. Usually the way it worked would be people would discover a class of vulnerabilities, and then someone would come up with a header that could defend against that class of vulnerabilities. Then another class of vulnerabilities would pop up, and another header would come out. And this went back and forth, and as you can imagine, as these standards or pseudo-standards evolved, it wasn't really documented or tracked together all in one place what tools you had and what headers you could use to defend your site. So that's what I'm talking about today, is all the headers you have in one place, and hopefully you'll draw upon some things that make your sites more secure. I'm going to start off talking about cross-site scripting. This is the most common vulnerability that we see at Box, and I think that's probably the case for many of you in your organizations. There's a couple of headers that can be used to defend against that. Cross-site request forgery is another one on the OWASP top 10. Clickjacking comes up from time to time. There's a couple of ways that are fairly effective at defending against clickjacking. Then I'll talk about sensitive data exposure, number 6 on the OWASP top 10. How you can enable web APIs with cores. A couple more areas talking about things that are a little bit still developing. Hosted untrusted content is fairly straightforward, but there's some tools you can use to make that safer for your site. And then there's some emerging standards that are under discussion and not yet available, but may change the way that we manage sessions in the future. All right, so cross-site scripting. Cross-site scripting, an attacker runs code on your site. He can do anything that a user can do. So this is fairly serious. It's essentially account takeover. And we want to do anything possible to prevent against this. Like I said before, it's very common. It's number 3 on the OWASP top 10. There are 3 main forms of cross-site scripting that are classified. There's reflected cross-site scripting, where something sent out in the request from the browser gets echoed back to the user and then executes in the page. There's stored cross-site scripting, where something in the database or maybe pulled from an external resource by the server is then rendered in the page and causes the script to execute. There's also DOM-based cross-site scripting. So this is where scripts are being assembled on the client side, and pieces come together in such a way that some new script is rendered that executes under the attacker's control. So the best tool we have here to go against the reflected cross-site scripting is a header called XSS protection. This is something that was invented in IE 8. There was a time when IE was actually at the forefront of web security, believe it or not, and this is something that they introduced and that then was later adopted by all the other major browsers. So this is designed to protect against that reflected cross-site scripting, where you see something in the request and it comes back in the page. That's a pattern that's generally dangerous, and so by default, that will be stripped out of the page. Now, unfortunately, stripping content out can cause problems, because if there's something before what gets stripped out and something after what gets stripped out, and they merge together, that can be something dangerous too. So after people figured out that was an attack vector, there's another attribute called mode equals block that was introduced, where instead of just pulling out the malicious content, if the page looks like it might have cross-site scripting in it, it just won't render at all, and you get a blank page. There's unfortunately one danger of doing it that way. There's a series of steps the attacker can use to capture the document refer in that blocking mode, but I would say generally allowing the script to execute is more severe than that information exposure, and so I would recommend using the blocking mode, even though it does have that limitation. All right, so here we've got an HTTP request. Simplified a little bit, fairly standard. Send it out asking for index.html, and you get back a response that would have these headers and also a content payload. So if you're sending the XSS protection header, you can just send it in response like this, and that tells the browser, if you see this script that occurs in the request you send out and in the response that comes back, block that page, display a blank page. So I'm going to go and give a little example of this so you can see how it works. So I've got a very simple web application here. And turns out that you can send in your own input there. And so it's not just hello world, it's hello whatever I want it to be. And if I'm feeling malicious, I can actually send some script into the page. And as you can see, that started executing. So this would be a cross-site scripting attack of the reflected form, where something I sent in the response is echoed back in the page and then executes. In this case, I've told my web application to disable that default protection that you get from XSS protection. So that's why the script actually executed. But I also have a flag here that I can turn on that puts that protection back in place. And once I've done this, you can see Chrome's giving me a little message saying that XSS auditor refused to render that content, execute that script, because the server sent XSS protection header. And similarly, if I were going to turn on that blocking mode, you see you just get a blank page. There's nothing at all, so there's no chance that that script would be able to execute. All right, moving on to our next defense against cross-site scripting. This is content security policy. So CSP is a W3C standard. It allows you to control which resources are being accessed by a website. So you tell the browser, these are the resources you're allowed to access. You can't go look at anything else. It also has a nice property where if the browser detects that it would be violating that policy that you sent down, it can actually report back to you and tell you, hey, you had a policy that said, I can only load images from this particular origin, but I tried to load one from somewhere else. Here's what happened. So this is a really great property because it allows you to set up in report-only mode, watch what happens, and then tune your policies accordingly to reflect the real behavior on your site. I really love this. It's also great to imagine what would happen if children worked this way. You'd be like, hey, kids, no video games after 9 p.m. And then the next morning, Mom, Dad, I snuck downstairs and played some video games last night. It'd be pretty cool. All right. One of the challenges of this as a developing standard, which it really is that you can't just send one header and get coverage everywhere. I don't know if any of you remember back in the days of IE4 and Netscape 4. Some of you have probably been around that long, where you had to write your code for one browser and then you write your code for the other browser. Well, this is that in effect all over again. I suspect over time, all the browsers will converge on what's now the defined standard, which is the content security policy header. But for now, if you wanted to get complete coverage, you would have to send 3 different headers with the same policy information in them. One to cover newer versions of Chrome and Firefox, one to cover IE and older versions of Firefox, and then one to cover the web-based browsers, Safari and the older versions of Chrome. So content security policy allows you to control over any external resources that your site may be pulling in. Things like scripts that are executing, embedded media, images, custom fonts. I recommend that you start off and use a simple policy that will mostly report and shut down things you absolutely don't want to use. So for example, if you run a financial services website, it's unlikely that you'll have embedded audio and media in your site. So you could say media none. You're not allowed to execute media. And then if for some reason there were a vulnerability in the media player, an attacker wouldn't be able to get code into your page that would load media. This also will give you a chance to get familiar with content security policy, learn about how it works, and then potentially use some of the more powerful features that would allow you to shut down scripts in the future. So this is what it looks like when you're deploying a request. We've got our familiar HTTP request, and in the response, the server sends some directives explaining what content is allowed to be executed in that page. So here we've got something that says this page is not allowed to run JavaScript, and if you see any violations of that policy, report back to me, make a call to this URI. One note that I wanted to make in terms of practical application, to really get at cross-site scripting, you want to set up a policy that says all of your scripts must be loaded off of the server and get any script inline in the page moved away. And that way, if an attacker injects script into your page, the browser can say, script in that page is not allowed to execute, block that as a policy violation. This can be challenging for those of us who are developers. Developers, and especially web developers, like to move fast. We like to get code out. We like to get it working. And the practice of writing code only in script files that are included rather than code that is inlined into the page requires a little bit of adjustment. So something to be aware of, that there may be some cultural adjustments in your organization before this is something that you could adopt. I think it's relatively new. It's very promising, especially because of that ability to report back on policy violations. And so I think everyone should keep an eye on this as it makes its way out into all browsers and gets more broad support. I suspect it's going to be one of the most powerful tools we have against cross-site scripting. All right, moving on to number 8 on the OWASP top 10. This is cross-site request forgery. This is where the attacker drives the browser to do something the user doesn't want to do. It leverages the fact that people may be using multiple sessions at the same time. So I might be logged into my webmail, and then I go surf to some other page. And if I happen to hit an attacker's page, the attacker can send a request that says, oh, delete my webmail account over to the webmail server. And because I'm logged in at the same time, the browser will happily send along my cookie with my session on it, because that's the way that the webmail is going to track sessions. And unless the webmail server has some protection saying that only its requests should be honored, it'll let the malicious page send that delete account over, and I won't even know it happened. This is typically handled using a random token, something that would be embedded and sent along with the request, either something random or an HMAC. And then the server verifies that only sites that have that token are making legitimate requests, and all their requests should be discarded. There's an HTTP header called origin that the client sends along that can also be used for this same protection. So the server would look and see if the client sent an origin that was allowed to make requests on that server, the request would be passed through, and if the origin were anything else, it should be blocked. So here's what an origin header request looks like. This one comes from the client, so the browser is automatically going to be sending this along whenever it's trying to make a request for one of those external resources. And the server can look and see, okay, is this coming from my site, or is this coming from something I don't know? And so in the delete account example, if you got one of these requests with an origin from attacker.com, you would say, no, I'm not going to delete that account. This is a CSRF request, and it's not a legitimate one. So the next class of vulnerabilities I wanted to talk about is clickjacking. In clickjacking, legitimate user interactions are sent to have unintended consequences. Really, this is user interface bait and switch. The user thinks he's doing something else, and in fact, he ends up doing something he didn't want to do. So the classic way that this attack is exploited is you'll have a page, and the victim site is put into a frame on that page, and then the attack site will render that frame completely transparent using style sheets. So it's there, you just can't see it. And then the attacker will put something else up that the user actually sees that drives him to do certain user inputs. Maybe type something, maybe click here, click there. And he aligns those clicks that he's tricking the user into making so that they're not sent to the attack page, they're actually sent to the victim site. So the user thinks, oh, I'm trying to win a prize, or I'm trying to play a game by clicking here and typing there, when in fact those requests might be sent through to another site in a frame that are deleting his account or making a balance transfer in a banking application, something like that. Because of this, the easiest defense is to control the way pages can be framed. So we have an HTTP header, another one that was introduced in IE8 called xframe options. And by setting parameters on this header, you can control whether or not your site is allowed to be placed into a frame. So there's four main options. Deny says, no, I don't want to be framed. Same origin says, you can frame me, but only from pages on that same server. Allow from allows you to specify a particular site that can frame you. And then allow all is saying, all right, anyone can put me in a frame, no big deal. Probably something for ad networks or perhaps some kind of embedded plugin. I think it's kind of cool. This is, as I mentioned, RFC 7034. I wanted to say that it was the very newest RFC because it was approved on October 10th as an informational standard for how browsers behave. Unfortunately, there's been 3 or 4 other RFCs that snuck in since then. So it's almost the newest, but it's not quite the brand newest one. So here's what it looks like if you're sending back xframe options deny. It's pretty simple. It's all right if you want your site to be framed with someone to pass that along in as a query parameter, validate it on your server side, and then send back a same origin allowing that site. Because the attacker can't control that parameter being passed, and it's going to be on your whitelist. So you would only say, these sites can put me in a frame. I recommend using this everywhere. It's pretty simple. Usually you know when your site wants to be framed, and you're not cutting off a lot by blocking framing if your site isn't intended to be put in a frame. All right, so I'm actually going to do a demo of this one as well. This is going to be a live demo on a financial services website. OK, so we've got a very powerful financial services website from Fort Knox Bank. And you can see I can click and perform a transfer of $1,000. It's good enough if I want to do that, but unfortunately, this is vulnerable to that same attack vector where the site could be put into a frame, and then I could be tricked into making that transfer. So you imagine you make this site a bit more transparent. This is, I think, 20% transparency, but the attacker could make that site disappear completely. And then you can go in and put something else over the top of it. So if I can trick the user to go into my page and say, hey, look, I can get a free iPad. That sounds good. I'll get one of those. And I click on that, but in fact, it didn't win me an iPad. It actually transferred that $1,000 away because my click was sent to the victim site and not to the iPad site. So this is where you can see the xframe options defense in play. If I turn on that xframe options deny header, you'll see that the framed site refuses to load. It no longer shows up. And the browser will tell you that it's refusing to display that content because the xframe options deny had been sent. So one thing I want to point out is that the most common way to do clickjacking is through that framing attack, but there are other ways to send user inputs in the wrong place. You can make the windows move around. You can pop up new windows in place. So there's a standard being developed by the W3C called UI safety extensions to content security policy. And so these are similar to the existing content security policy directives I've mentioned that control what resources can be loaded on a page. But in this case, you can set whether or not a site can be framed. And you can also say that user input, like clicks and keyboard presses, don't get sent to that site until after it's been fully visible for a certain period of time. So you might say, my site doesn't want to receive input events until it's been visible to the user, fully displayed for 800 milliseconds. And that way, if the windows are jumping around or if the site's been obscured somehow, those user input events won't even trigger on the site, and so the attacker wouldn't be able to take advantage of them to cause the user to do something he didn't want to do. All right, so number 6 on the OWASP top 10 is sensitive data exposure. Covers several things dealing with not encrypting your data either at rest or in transit. There's an attack on this that's fairly common called SSL stripping. So a lot of the times when you're working with a web application, say a shopping app, the user will have a bunch of interactions with the site, clicking around, browsing for items. And then after he's filled up his cart and he wants to check out, then the site will transition into HTTPS and use that secure transport only for the part of the transaction where the credit card and the sensitive information gets transferred. Unfortunately, if there's an attacker out there performing a man-in-the-middle attack, he can watch all that shopping happen. He can see what items the user's putting in the cart. And then right at the moment that the user wants to transition over to use the secure transaction, the attacker can jump in and start to change things. Because we didn't have the confidentiality check that you get from the encryption. We didn't have any integrity check. And so the attacker can actually jump in and just strip out all of those HTTPSs and turn them to HTTP. An unwitting user might go through and enter his credit card information anyway, not realizing that the transaction isn't being sent over a secure channel. So there's one other related problem, which is even if a user knows about the security, he might not do what's in his best interest. So I don't know if any of you, how many of you have clicked through on some browser security warning? You know, certificate doesn't match, it's expired. Most of us have done that. You just want to get to the page and get your work done. Unfortunately, in certain situations, this is a legitimate attack, and the user is shooting himself in the foot by going past those warning messages. So this has been dubbed click-through insecurity, where in spite of the efforts of the browser to warn the user you're doing something dangerous, he goes and says, I don't care, I need to get my job done. Sometimes as a site operator, you don't want users to be able to opt out of security in that way. So introduce strict transport security. So this is another IETF RFC 6797. Strict transport security is a way to handle both of these problems. It requires that the browser prevent opt-out, and it requires that every connection made to the server after you've started strict transport security is over secure transport. So if there's a request that was originally supposed to be HTTP, and the browser has previously seen a strict transport security header to that site, it will seamlessly convert that to be an HTTPS connection and use the encryption and the authentication when talking to that server. So this is pretty nice for things like banking sites or for Box, where all transactions that the user is having ought to be over a secure connection. You can just turn this on, and then once the user visits the site for the first time, he'll be locked in and he won't be vulnerable to those SSL stripping attacks if someone can get in the middle. All right, so strict transport security looks something like this. It's just one header. You set a max age saying for how long you want to impose this requirement on the browser. The browser will cache this. It's essentially a TTL counting down. So if the user keeps visiting your site, you keep sending the header, that TTL will be extended. In this case, we're saying use SSL when talking to me up until 1 year out. And so as long as the user comes back within a year and you get another one of these headers, he's always going to be using that secure transport to visit the site. There's another property that you can set here as well called allow subdomains. So by default, this applies only to the server or the origin of the request. If you set the allow subdomains, it says also apply this strict transport security policy to any of the subdomains that you might have under mine. So I recommend deploying this aggressively. In today's day and age, the overhead of SSL TLS isn't that great. A lot of our sites are dealing with sensitive transactions, and we want our users to be protected. And there's, I think, very little downside to putting this in play if your site is primarily available via HTTPS. All right, so a related technology dealing with SSL and TLS transactions is the idea of certificate pinning. So this is a way of defending against a different attack vector where everything about the SSL transaction may be legitimate, but perhaps the certificate authority has been compromised. So the way that initial trust is established between the client and the server is that they'll present a digital certificate that asserts their identity. Now, if the assertion is backed up by someone who's vouching that that user, that server, or that client is who it says it is. So there are trusted parties like Symantec or Microsoft or Google that issue these certificates that essentially say, I am who I say I am because that guy said so. And as long as you trust that guy, it's a pretty good system. The problem is if there's an issue with the other guy where perhaps his key gets compromised, then the attacker can go and issue new identities pretty much at will. And there's no way for the client to tell that those new identities aren't valid because they're still tied back to the trusted identity that got compromised. So introduce certificate pinning, or actually, more accurately, public key pinning. So this is a draft IETF standard that's being discussed right now that allows you to specify a hash of the public key that you're going to use in your SSL TLS transactions. And so that says this particular key is the one that I'm going to use. So if you see one that comes from a trusted authority, but it isn't this key, you want to ignore it and throw an error message. This one inherits the nice property that content security policy had, where you can report back to the server on violations. It also requires you to set 2 pins. One of the challenges is that if you ever have a problem and you need to refresh or renew your certificate, you don't want all your clients to not be able to talk to you any longer. And so it's important that you have 1 pin as your primary and 1 as your backup, and then roll over between the 2 of them. Once you've moved over to the backup pin, you put in another backup and promote to primary the one that you're currently using. I think this is something that we should keep an eye on. I also think that the risks are pretty high here. So I recommend against using this until it's become a little bit better adopted and there's wider support. I think it definitely solves a problem, but the risks of having your site go down because you set your pins wrong is really too high for most of us to take on. So here's what the certificate pinning header looks like in action. You set that public key pins. There's a max age similar to the strict transport security, which is a TTL counting down how long this information should be stored. And then in this case, there's a couple of pins for 2 different public keys. And of course, the report URI where violations would be sent. All right, the next area I wanted to talk about is not really a security feature or a security header. It's more of an insecurity header, but it's still very useful. So cross-origin resource sharing, or CORS, is a W3C standard that's used to enable web-based APIs and mashups. So much of web security back from the beginning of scripting has had a model where you have what's called the same origin policy. So scripts are only allowed to communicate back to the server that sent them, presumably saying you can trust yourself, but don't trust anybody else. Unfortunately, with web pages or web APIs, sometimes you want 2 pages to be able to interact and talk to one another. This is great for creating mashups or sites that interoperate with each other, or REST-based APIs that can be used to power web applications. So with CORS, it's a way of saying you don't have to follow the same origin policy always. A server can individually opt out of that if it wants to. So the way this works is the browser will make a cross-origin request to the server. This happens regardless as long as it is what's called a simple CORS request. That's something that uses get, post, or head and has a standard content type such as text plain or something that's containing form data. The server receives the request, and if the origin sent along in that request is one that it wants to allow as a cross-origin request, it sends back a response with this access control allow origin header saying, yes, browser, this origin is legitimate for cross-origin requests, please allow it. The browser gets the response, and if the origin matches the one that it requested, it gives the JavaScript layer access to the content of the response. If the origins don't match, the browser prevents the access to that content. So an interesting thing here is the request is going to happen regardless, but the response may not be made available. This covers the case of simple cross-origin requests, but sometimes, actually often, you have web APIs that are more complicated. They may be using other HTTP verbs like put or delete. For those, we have additional protections that are required before the browser is allowed to make that request. It's called a preflight check. So any kind of more complicated request has to go through preflight first. And that means sending an options request over to that endpoint, requesting access. And then the server responds and says, yes, you're allowed to access this endpoint cross-origin. Here are the methods you're allowed to use. And then the browser will make a second request, the actual request with the put method, and then get the data back in the response and expose it to the script layer. There's a few other things that you can pass with additional headers. There's access control request credentials, which says whether or not cookies should be sent along in that cross-origin request. There's access control request headers, which says, I want to modify the headers in that XML HTTP request cross-origin. Am I allowed to or not? And there's access control expose headers, where the server can send back a message to the browser saying, all right, here's my cross-origin response. And there's some non-standard headers in this response that I want you to be made available to the script layer. So for example, if you have custom headers that your web API is returning that have critical information, you'd send back an access control expose headers with the name of those headers saying that the browser should allow access to them when it makes a CORS request. There's a couple of things to think about when implementing CORS. First off, you're getting that origin header, but it's pretty easy to spoof. I could fire up curl and make a request to your server with any origin I want. So don't rely on origin for access control. Just check that to see whether or not you should be allowing a cross-origin request. The second is something I call promiscuous CORS. You can send back access control allow origin star, which means that anyone is allowed to do a cross-origin request to your site. The reason I recommend against this is because you don't necessarily know where that site is running or how it might be protected. And there are certainly cases where a site that's sending this allow origin response could be on your intranet. In that case, if it's sending access control allow origin star, it means that anyone can make requests to it. If you have a user on your local network, he might hit an attacker's page on the internet, and that attacker is allowed to make a cross-origin request to your internal site. And so there's a good chance in this scenario that some data might leak out that wasn't intended. So it's better just to whitelist the origins that you explicitly approve and not just open it up carte blanche. So some sites have to deal with user input. Most sites do. Some sites deal with untrusted user input that is actually in the form of files. So this is something that Box deals with all the time. Users are uploading files to store and share, and we're going to be delivering those back to other people. It's important because of that same origin policy that any of that untrusted user content isn't treated as if it were coming from your domain. And there's a few tools that allow you to completely segregate that. This is a little bit like a glove box for untrusted content. With access control, with X content type options, this allows you to say, I don't want you to try to guess what type of content I have. So there's a very nice behavior in IE in particular, but also other browsers, where they'll look at the content that comes back and try to guess how to render it. So if your server sends a response with content type text plain, and then there's a bunch of HTML, Internet Explorer will look at that and decide, well, that looks like HTML. Clearly, you meant for me to execute that and render it. And so if there were script in there, that script would be executed off of your domain. Fortunately, there's a way to turn that off, and that's by sending X content type options no sniff. And that tells the browser, Just obey the content type I told you. Don't try to guess what it's supposed to be. X download options is related. It means that when a page comes and the file download box appears, don't allow the user to open it in the browser. So this forces it to go bypass the browser and reduces the chances that the user might choose to open a potentially malicious HTML file. And the last one, the content disposition, allows you to force a download as an attachment. So if you say content disposition attachment, instead of rendering the page at all, it'll go straight to the download dialog and be delivered to disk. So you can use all three of these together. It looks something like this. Content type options, no sniff. Download options, no open. Content disposition attachment. So here, user was making a request for index.html, and because of the content disposition header, it would be delivered to the disk as a download in the file download.html. So the last thing I wanted to talk about today deals with OWASP Top 10 number 2, broken authentication and session management. So most websites use some form of cookies to track sessions. HTTP is inherently a stateless protocol, and so you're making a series of requests. You want to track that those requests are associated with each other in some way. And the best tool we have today is cookies. You have some unique identifier in the cookie that gets sent back and forth, identifying that user or that session. Unfortunately, the cookie is really just a bearer token. Whoever has the cookie, whoever has the token is the person. And that's not the best security model to have, because if it gets stolen, anyone else can assume the identity of that session. There's a few things that are under discussion to try to solve this problem by building a better way of maintaining sessions into the HTTP protocol with some extensions. The first I'll mention is session continuation. So that's adding new headers that will be used specifically to manage sessions, and they won't have this property that they're a bearer token. The second is the idea of an origin cookie. This was proposed a few years ago by Andrew Bortz, who's now at Dropbox, Adam Barth, and Alexei Cheskis. I don't know if that's exactly how you say it. But the idea here is that the cookie is tied to a particular origin server, and if someone else tries to send that cookie, the browser would not send it along. And then the third idea is something that's proposed by Dirk Balfons at Google, which is called channel ID. And this is a way of tying a session or attributes of that session back into an SSL TLS connection. And so if you have that information stored along with that SSL TLS connection, you can't steal it and use it somewhere else because it's cryptographically bound to that channel. It's not clear which of these will win. They all have merits. They all have things that are not so good about them. But the point is there's discussions going on about how we might better manage web sessions. I encourage people to keep an eye on that and be able to take use of it when it actually comes out and starts being supported in browsers. So in summary, I wanted to go over some recommendations for all of you. XSS protection, one mode equals block. I think you can use that everywhere. It's pretty safe. Occasionally, you might have false positives if your site is actually trying to send data that will be echoed back in the page. But generally, just use it everywhere, and it will protect you against some cross-site scripting attacks. Content security policy. I think this is something to play around with. Get to know it. Be familiar with what it does. Set up a simple policy and establish that infrastructure so you can start getting reports back. And think about moving your organization to using this in the longer term as it becomes available across more browsers and is better standardized. Block CSRF either by validating the origin header or by using something else like randomized tokens in your application framework. I think X-frame options deny. You can also deploy pretty widely. There's pretty much no harm to sending that response back. It'll protect you against clickjacking attacks, and you tend to know when you want your page to be put into a frame, and you can adjust the header accordingly in those situations only. Strict transport security, I'm a big fan. I think if your site is primarily using secure transport, or you can support primarily secure transport, you should be turning on strict transport security. Lastly, X content type options, no sniff. you can pretty much send this everywhere and have your server send back the correct content type. There's no reason for the browser to be guessing as long as you have things configured correctly on your side. So these slides and a resource deck with references on all the topics is available at the URL here. If you have any questions, I'm happy to answer them by email, also in person in the room.